Skip it up and that up.
I'm back. Yay. And now I'm doing another one of these videos because, as a teenager, it's my utmost responsibility to destroy my sleep schedule. But hey, this one's only supposed to be 7 minutes long. So maybe this time it'll be different and I won't spend way too many hours that I should have been sleeping overcomplicating literally every aspect of the video and putting in random stuff to make it more entertaining. Yeah. Hey, it's post-editing, Austin. And you wouldn't believe it, but I spent way too long on this project. Again. Oh yeah, right. There's a topic I should be going over. The topic of today's episode is about the universe growing, and growing, and growing. I think I'm sensing a pattern here. Okay, let's get started. Shockingly, the video on the development of the universe starts out when the universe began.
No way!
And yes, I did reuse that joke from last episode. What did you expect? Quality content? So, around 13.8 billion years ago, the universe was originally an infinitely small and dense speck called a singularity, which held all the matter in the universe. Eventually, the singularity began expanding outwards incredibly quickly, in an event called the Big Bang. And the universe is still expanding to this day. And that's a wrap. Yeah, but it's not that simple. Since the universe has a bunch of phases, each with their own quirks that all need to be covered enough that it would make Verizon proud. Okay, to start things off at the beginning, the Planck epoch is the earliest known period of the universe. It went on from right after the Big Bang to 10 to the negative 43rd power seconds. Before this, the universe was still nothing more than an extremely hot and dense singularity. However, this would quickly change as the state of the universe got more and more unstable, and it began to expand and cool. More specifically, the universe would expand from a singularity to 10 to the negative 35th power meters and go from being infinitely hot to 10 to the 32nd power Kelvin. The conditions were so rough that none of the basic particles of matter would bind together, and light itself hasn't formed yet. At this time, the universe is nothing more than a speck of pure energy. Next up is the grand unification theory epoch, or GUT for short. It went on to 10 to the negative 36th power seconds after the Big Bang. The temperature is around 10 to the 28th power Kelvin and has increased in size so little that it's barely distinguishable from that of the Planck epoch. Particles still couldn't bind, and light still hasn't formed yet. While this all sounds pretty similar to the Planck epoch, the GUT epoch does have something worth mentioning, that being the status of the fundamental forces. Due to the universe cooling, gravity separates from the other three fundamental forces, which have remained unified. Well, for now at least. Next is the electroweak epoch, during which the universe begins its rapid expansion, called inflation, with it now being around the size of a grapefruit. It went to 10 to the negative 12th power seconds after the Big Bang. At the beginning of the electroweak epoch, the temperature had fallen enough for the strong nuclear force to get frozen out from the other fundamental forces, which released a lot of energy in the form of a repulsive force that led to the inflation of the universe. Towards the end of the electroweak epoch, this inflation caused elementary particles like the Higgs and W and Z bosons to form and be thinly distributed throughout the universe, and eventually decay due to the lowering temperature. Also, the temperature drops low enough that the two remaining unified forces could separate, with those forces being the electromagnetic and weak nuclear force. And for those of you not keeping track, we now have all four fundamental forces in their current forms that we know them by today. Next is the quark epoch, which has the universe get filled with quark-gluon plasma containing quarks, leptons, and their antiparticles, which is just a fancy way of saying that the subatomic particles that make up atoms now exist. It went to 10 to the negative 6th power seconds after the Big Bang, was around 10 to the 12th power Kelvin, and grew slightly larger than it did previously. After that was the Hadron epoch, which had the universe drop to 10 to the 10th power Kelvin, which was cool enough for the quark-gluon plasma to form into hadron and antihadron pairs, which are particles made up of two or more quarks. As the temperature continued to drop, the hadron and antihadron pairs stopped being created, and the majority of them annihilated each other through reactions which resulted in the formation of high-energy photons. It didn't experience much notable growth and went from 10 to the negative 6th power seconds to 1 second after the Big Bang. Yeah, that all happened in 1 second. And we're not done yet. Crazy, I know. Then came the lepton epoch, which basically did what the hadron epoch did, but with leptons instead of hadrons. The lowering temperature led to the formation of leptons and antileptons, with most of them eventually annihilating each other after the temperature got low enough and creating high energy photons. It went from 1 second to 10 seconds after the Big Bang, and it still hasn't grown that much bigger than it did previously. Next is the nucleosynthesis. That's a big word. Next is the nucleosynthesis epoch, which was when the first nuclei began to form. Immediately after the lepton epoch, protons and neutrons began to form into the nuclei of hydrogen, along with some helium and a little bit of lithium and deuterium. How do you say that? Whatever, I'm not re-recording that. It went from 10 seconds to 3 minutes after the Big Bang, which gave it plenty of time to grow up to 600 light years in diameter. The temperature went from 10 to the 9th power Kelvin to 3000 Kelvin, after which it got too cool for fusion to occur. Following that is the nuclei epoch, which didn't do much differently than its predecessor did over its 500,000 year runtime. It was still too hot for nuclei to bind with electrons to create atoms, and while light did form, due to the universe's high density, it was also opaque to that same light. Though it did grow to 600,000 light years in diameter during this epoch, so it's got that going for it. Then there was the atomic epoch, during which the first atoms formed from nuclei and electrons through a process called recombination, and light is now visible. And to close things out, the galaxy epoch sees the formation of galaxies and stars in locations where enough matter can be drawn in by gravity to create them. Also, stars produced heavier elements not originally made in I hate this word, nucleosynthesis epoch. And the universe is still expanding, and we're still in the galaxy epoch to this day. And that's a wrap. For real this time.